question. How do we know if we're using a reasonable collective variables? That's the meaning. That's the $1 million question. Like, so as someone said, that's the $1 million question. Is and meaning I was recently in a workshop that basically on that issue, how to find collective variables. So it is not easy. It's definitely not easy to find a good collective variables. So, but like if you're using, let's say, physical intuition, normally you need to do a bit of trial and error. Is that you kind of you introduce some collective variables, and then you try to, let's say, initially you would probably look at unbiased simulation to make sure that they separate the two states, and then you might try to use this collective variable to let bias the simulation. And then what happens is that you might be lucky and you kind of see a lot of transition and everything is working fine. Great, you have a good collective variable. But often what is happening, you might see a behavior like shown here, like this kind of hysteresis behavior. And you might see that, okay, this would indicate that it's not working well. Or you see like no transitions at all. So then you normally need to go into your system and maybe take a look at your system to maybe try to identify something that you're missing. And of course, this is difficult and it's like a bit system specific, but there's no, I would say, clear answer about that. And of course, not only nowadays, people are trying to use like machine learning methods for doing this, somehow do it on the fly. Maybe you learn a machine learning collective variable from the bias simulation and so on. So that's of course, let's say, yeah, but as I say, you would normally see, like, if you have a bad collective variable, ideally the collective variable is so bad that it's not working at all, then you could just forget about that one and try another one. But let's say, yeah, I mean, it's difficult, and like it's a lot of effort in the field is focused on, let's say, solving this problem, either by like identifying generic collective variable for a set of problems, could be, for example, for biomolecules or protein ligand binding, or like let's say materials and so on. Okay. Yeah. As I say, okay, there was a related question, but let's say automated way to capture reasonable collective variables. As I say, there's a lot of methods focused on machine learning for collective variables. I haven't had any reviews on that, but I can add links to reviews of collective variables for machine learning for collective variables in the GitHub. Okay. How long should the Gaussian bias be applied? Yeah, I mean, normally you would run it until convergence, and normally you would maybe want to run a bit longer to make sure that you kind of sufficiently convert the simulation. You would need at least need to see quite a few number of transitions between the two states. So I can maybe say in general, let's say, to assess convergence of metadynamic simulations, there are a few things that you should look at. You should look at that the Gaussian hill height is gone to 0, that you see a lot of transition between the two metastable states. You should calculate the free surface directly from the bias potential, and you should calculate it from reweighting, and should compare the two results. And if they are in good agreement, that's most likely you are reaching convergence. Okay. In the Allen dipeptide example, so in the Allen dipeptide, I was using molecular dynamics. Most example where I know of use metadynamics with molecular dynamics. You can, of course, use metadynamics with Monte Carlo sampling. In that case, you can probably add the Gaussians more frequently, and so on. And also, if you're using metadynamics with Monte Carlo, you don't need to think about the derivatives of the collective variables. So you can use different collective variables there. And let me see. Someone asked him about, let's say, okay, here, when I talk about like how often we add like the Gaussian, I would say 500 to 1,000 empty steps. And that would be around that will be around 1 picosecond, because let's say if you're using like a time step of 2 femtosecond, this would be like 1 to 2 picoseconds. Okay. What Monte Carlo codes are parsed or compatible with Fluent? It's a good question. I have to admit that I'm not really aware of any. In principle, you can like do it with patch it with molecular dynamics code. It's just a question of yeah. For Monte Carlo codes, you just need to pass the bias back to your Monte Carlo code, so you can do it in principle. Okay, how do you determine the collective variable is fast and slow? I mean, that's the same as, let's say, for finding this collective. Like most of the time, like a fast collective variable is something like that. It's like maybe a bond vibration or something like that, or something which happens on a much faster scale than like the other, let's say, the slow process that you're interested in. What problems could arise from non-orthogonal collective variables? What do you mean by non-orthogonal collective variables?
Suppose you were using a contact matrix between a dimer and the distance between the geometric means of both proteins.
So you mean that the two collective variables are like directly correlated?
Yes.
Per se, in practice, I don't think it's a big issue. I mean, you will be adding bias like maybe twice on. So, like, say if you have a contact map, which is like a contact map with distances, then you have another collective variable which is just one of the distances. That was what they were saying.
Yes.
That I think should work fine. Meaning, I think you might add, because the contact map will average over the distances when biasing, while in the other case you add bias directly. So I don't foresee any big problems. I mean, there's a good discussion about this in the so-called paper by Giovanni Bussi about replica exchange with collective variable tempering, where it discussed this in the SI. And I think what you're doing is basically you add the bias twice. You might have a stronger bias on the collective variable, but it doesn't make any difference. So you could also think of like having the collective variable twice in your metadynamics. It doesn't really make sense, but I think it will not really make any huge difference. Okay. Okay. So I'm not totally sure if I managed to catch all the questions. Some of them have already been answered. I will add maybe a few like reviews about, let's say, machine learning for collective variables. Okay, so there's this final question: how can we solve the problem of hysteresis behavior of CVs when we try to bias contact map with OPES? Meaning, I haven't used OPES myself. It's a different method, but if you have hysteresis behavior, it probably means that your contact map is not sufficiently good enough. Then you might try to find other collective variables. That's maybe there are some other collective variables in the system that let's say you will need to look at. That's a bit difficult to answer, let's say, without, this can be a bit system specific. So if I would have the, let's say, could do a 1 hour tutorial to how to find collective variable for any given system, that would be great, but that's not how it really works with this method. So so I would try to show you how you can apply these methods now to like a simple system in a case where we know the collective variable. Yeah. So I think we should take a 10-hour break, and then we'll start with the I will start with the tutorial. So I think we'll start, let's say, 10 minutes past. 10 minutes past. Okay.